Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into section 3.4 in the Big Ideas Math Integrated Math 1 textbook. This is graphing linear equations in standard form. Now, you haven't seen standard form before, or at least we haven't graphed out of the form, used it for our ways. You know y equals mx plus b? We're not graphing out of that one yet. We're actually doing that next section, and we were using y equals mx plus b in a way because we would plug in numbers for x and get values out for y, and you can always use a table in the way that we've been doing it to make graphs of any kind, not just linear equations, for quadratics and things you're going to learn in the future, right? But there's also a standard form. It's more of an official appearance that linear equations have, and quadratics and stuff have them too. But it's more of an official appearance that we're going to use, and we use a different method to get the graph thing out of. And I think you're going to like it quite a bit. It's going to be a useful method, as well as you're going to like y equals mx plus b. Trust me, you will. But we're going to start with this one here. It's a shorter section. I think 36, maybe 38 questions. I can't remember which one specifically. Somewhere in the 30s. But we will be graphing. So if you do need graph paper, you can jump to the description section down below here, and you can download a PDF of the graph paper. 6 graphs on each side. 6 and 6 give you 12 for a single printout. So I don't know if that's going to be enough. Probably not. Have to do a couple printouts. Otherwise, use your own graph paper. Use your make your own scales, things like that. Also, of course, download the PDF of this section down below. And if you'd like to find the timestamps to specific problems, you can do so. I'm going to begin with the lecture portion, and I'm going to go ahead and get started with said lecture. We're going to graph equations of horizontal and vertical lines. Now, this can technically kind of be said to be out of standard form. That being said, it's not the official look of standard form, but we have to know how these things are graphed as a whole. Remember, not everything here needs to be functions. Vertical lines are not functions, but we can still graph them. Now we're going to graph equations in standard form using intercepts, and this is the key. Intercepts means we're only going to really plot 2 points at most, which means you really do need a ruler for what we're going to have. Keep that in mind. And x and y intercepts are 2 of the vocab words alongside standard form. And we're going to use linear equations in standard form to solve real-life problems, which means when we write our equation, it'll probably be out of standard form. The nature of the equation will be standard form-esque to make it so. So what does standard form look like? Well, they're talking about horizontal vertical lines here, but here's standard form. Standard form is ax plus by equals c. Now, anytime I tend to write it, I tend to have the a's, b's, and c's lowercase. I hope that's okay. But ax plus by equals c. Not the same thing as y equals mx plus b. Even the letters are different, and I want you to note that, well, that y and the x represent the same things. Those two variables are these two variables here. This b here has nothing to do with that b there. They actually are completely unrelated, and you're going to note that when we do y equals mx plus b. I'll make sure to differentiate between the two. But they're two different equations. Now, either equation is a form of a linear equation. So in section 3.2, when they said, an equation is linear when you can write it in this form, well, it's also linear if you could write it in this form. It doesn't matter which one. I understand the practice of this one, and furthermore, I endorse it. But standard form is also one that we can use. Now, they stated a, b, and c are real numbers, and a and b are not both 0. You see, if a was 0, this whole term would wipe out. If b was 0, this whole term would wipe out. You'd have no variables, just a constant. And if that constant's not 0, well, listen, you have no equation. You're not making a line anymore. A can be 0, but not b, or b can be 0, but not a, and you can still make a line out of what you have. C can be 0 at any time. It's unfortunate when it is, though, because of the intercepts issue, but we'll talk about that when we get there. Anyway, they talk about this consideration here. They say, consider what happens. Actually, let me leave that up here. Consider what happens when a equals 0 or when b equals 0. Hey, guys, when a equals 0, what happens? Or 0 times x is x, this term goes away. And you're going to see me do this a lot. I'm going to hide the term. It's like it's not there. The equation now says positive by equals c. That's what they're showing you here. They said, or y equals c over b. If you notice, you can divide both sides by b. You can divide both sides by b here, and you'd get y equals c over b. Now, that's not something to memorize as far as that c over b portion, but notice they say because c over b is a constant, and it is. Those are just numbers. It can be 3 over 2. It can be 10 over 5. Because it's a constant, you can write y equals, they say, lowercase b as your equation. I guess that's where they get to their lowercase variables, and I guess that's how they differentiate between b's. They have one capitalized. I don't. I'm an idiot, but that's okay. But they have this y equals constant equation. I might even use the letter k. You might hear me in different things use the letter k here. And x, I might put the letter h just to make sure it doesn't look a little weird. But similarly, when b equals 0, what if we do the same thing, but instead here we make b equals 0? Now the y term goes away, and you're just left with a times x equals c. And you divide both sides by a, and now suddenly x equals c over a, but you can also rewrite that as x equals a, or x equals h, or whatever you want to put. X equals a number. X equals a number. So y equals a number, x equals a number. No other variable involved. Well, these are the equations of horizontal and vertical lines. And by the way, remember, this is standard form right here. We're going to be doing a lot of the set these things equal to 0, and we'll talk about those. But when a and b are separately 0, we get equations like this. Y equals b is the equation of a horizontal line when the y value literally is b. It passes through the point 0b, and it goes flat across here forever. All real number domain. The range is limited to just the y value b. When x equals a, it becomes a vertical line just at the x value that is a. It hits a comma 0 alongside every other x that is a as y goes infinitely up and down. It's not a function, but it is a linear. It's linear. It's a linear equation, not a linear function. But it's a vertical line. It's a vertical line here. Now, before I move on to the examples, this is the part that I need to stress and make importance of. Maybe we can make sense of why these things are what they are. We will later, especially more so when we start doing y equals mx plus b form. But here, let's just talk about this. Because you see a y equals equation, when we think of y, we think of up and down, right? We think of up and down. So, Mr. Robinson, if y goes up and down, why does this graph go left and right? Well, hold on a second. The up and down portion is taken care of here. Consider this line, the x-axis right here. We want to graph y equals b. Let's say b is 5. It doesn't matter. Then we're going to go up to 5. We're going to go up to 5. There's the up and downness of that. We have to go up to the y value of 5. Because consider this. What are these points that are on the graph? If this was 5, here's a point on the graph that's 0, 5. Well, here's a point on the graph that's 6, 5. Here's a point on the graph that's negative 2, 5. Here's a point on the graph that's negative 10, 5. What do all these points have in common? Say it. Y equals 5. That's what they all have in common. Y equals 5. So that's why this equation works what it is. No matter what x is, the y value is always 5. As far as I go left and right on this thing, the y value is always 5. That's what that means. That's why that is. Now, x equals equations are the exact opposite. X equals equations are exactly the same x the entire time. Let's say this was x equals 3. X equals 3 here. Mr. Robinson, I thought that x's go left and right. They do. Starting from the y-axis, we can go right 3 units over, 1, 2, 3, boom, and then we have all of the values of x that are 3, including 3, 0, 3, 3, 3, 8, 3, negative 2. What do all of these x values have in common? What do all these values have in common? These points? X equals 3. So no matter what y is, the x value is always 3. So that's the part that, yes, it confuses people. And remember, this is still the x-axis. This is still the y-axis right here. But y equals equations, when it's a constant, are horizontal, and x equals equations are vertical. Now, in a vacuum, you'll remember this. When we do the problem set, if there were 20 problems like this, you would get them so fast. A few sections from now, or if you're tested on it later, or a few chapters from now, whatever, it's still something to keep in mind. It's still a part of what we do, and it's something I'll just have to remind you of. I won't spend 10 minutes talking about why this is what it is. We'll just have to make note of it. So let's look at some examples. Graph y equals 4 and x equals negative 2. Y equals 4, we are going to go up to 4 for y. We can plot the point on the y-axis if you'd like to, but we're going to draw a horizontal line across. And they're showing you what I was showing you as well. For every value of x, the ordered pair x4 is the solution of y equals 4. No matter what x is, the y value is always 4. Draw arrows, make it linear, make it an all real number domain like that. X equals negative 2 is for every value of y, the x value is negative 2, starting from negative 2, 0, going up forever, going down forever. Here's your x equals negative 2 equation. Now I'm just going to use my line tool, and I'm just going to draw vertical and horizontal lines on my graphs, and that's it. Pretty quick examples, and that's all they mean. Now let's revisit standard form, and let's graph linear equations that are not horizontal and vertical lines. And we only need 2 points from it. And I stated this before. 2 points can make a line. For the most part, I'm going to ask you to plot as many points as you can fit generally. For the sake of standard form, I'm going to ask you to just plot 2 points and use a ruler to draw the line through those 2 points. Here we go. You can use the fact that 2 points determine a line. So if I can get 2 points out of any of my graphs, I'm going to be able to draw a line through it. You know what points we can find really easily out of standard form especially? The x-intercept and the y-intercept. The x-intercept is the value of x where you cross the x-axis. It's where the graph crosses the x-axis. It's the value of x when y equals 0. Think about it. On the x-axis, all the y values are 0, which also means, by the way, and they're probably going to ask a question here, graph y equals 0. Well, that is the x-axis because those are all the values of x when y equals 0, including any x-intercept on a graph. So when y is 0, x is this apparent a value. So that's the x-intercept right there. So in our equations, we can substitute 0 for x, 0 for y, and we can solve for x, and then we'll find an x-intercept. The y-intercept is where we cross the y-axis, and it's the value of y when x equals 0. The y-axis is also the line x equals 0. Remember, it's a vertical line on x equals equations. So when x is 0, substitute 0 for x and solve for y, and boom, you'll get a y-intercept. This is a really fast and easy concept to do, and it's really nice. It cleans itself up very well. So if you're in standard form, what's really nice about this is because x and y are on the same side of the equation, when one of them becomes 0 and goes away, you already now kind of have that y term by itself or that x term by itself when you set the other equal to 0, and you can find those intercepts real quick. So for example, you have the equation 3x plus 4y equals 12. I want to graph the equation, but I'm going to use the intercepts to do so. I want to find the x-intercept. I want to find the y-intercept. I want to find out what x is when y is 0. I want to find out what y is when x is 0. So I'm going to show you with the top equation what they're going to do down here as well. To find the x-intercept, we set y equal to 0, substitution. Now, what is 4 times 0? It's 4. It's 0. What is 3x plus 0? It's 3x. So to me, here's what I'm going to do a lot of. What happens when you substitute 0 for y? This term goes away. What does your equation now say? 3x equals 12. What does theirs say? Well, they didn't really write it, but 3x equals 12. They divide both sides by 3, and then they get x equals 4. 4 is the x value when the y value is 0. That means there's a point on our graph that is 4, 0. We plot that point right there. Okay, let's do it again. Let's do the y-intercept. The y-intercept is the value of y when x equals 0. So they substitute 0 for x. 3 times 0 is 0. 0 plus 4y is 4y. So what do I do when I substitute 0 for x, find the y-intercept? The x term goes away. You're left with 4y equals 12. Divide both sides by 4, and they get y equals 3. So that's the value of y when x equals 0. That means there's a point on our graph that's 0, 3. They plot it right here, and there you have it. 2 points make a line. I have my 2 points. I can use my ruler, draw a line through those points. Boom, I have the graph of this equation. I didn't need to get y by itself, make it y equals mx plus b form. I didn't need to substitute values of x from -2 to +2, especially when there's a fraction. Maybe I have to try some different values, plot all those points. I needed 2 points from it, from the most basic calculations ever. Remember, substituting something from 0 means that term effectively goes away. See how I'm literally crossing it out? I mean, in a class, I don't get to move this kind of thing here, and neither do you. So I would hide it with my finger, or I would just know what I'm doing with the problem. I'd hide it with my finger. I wouldn't actually cover it up like this, but for computer's sake, I could do that. Plus, you can't see me put my finger on the screen. So keeping that in mind, that's what happens. Those terms go away. Very, very easy to do. Solving real-life problems, let's see. We're going to come up with some sort of equation for a problem, or they'll build one for us, and we can interpret things. Modeling with mathematics. You're planning an awards banquet for your school. You need to rent tables to seat 180 people. There are 2 table sizes available. Small table seat 6 people, and large table seat 10 people. The equation 6x plus 10y equals 180 models this situation where x is the number of small tables and y is the number of large tables. And that's true. This does make an equation for it. If 180 is the number of people you have, and you can have 6 people per small table times the number of small tables, 6x is the number of people you can have at small tables. 10 people per large table times the number of large tables gives you how many people you can have per large table. The amount of people in small tables plus the amount of people in large tables equals the amount of total people. So they gave us the equation, but if we have to make our own, we have means of being able to do so. And hey, this is standard form. This is standard form. There are other things I feel like I could do with this standard form if I wanted to. I'm going to leave it. Like, I'm thinking of dividing everything by 2. I'm going to leave it. We're going to keep it like this for context sake. Now, they stated, graph the equation, interpret the results. For us to graph the equation, we'll do it simply by finding the x-intercept and the y-intercept. So for their, let's see, they're not showing much of the work, so I'm going to kind of do it very basically right here and mentally, if that's okay. You have this equation right here. I'm going to, for the x-intercept, set y equal to 0. When I set y equal to 0, that means that this term goes away. My equation now just says 6x equals 180. If I divide both sides by 6, I'll have found the x-intercept in this situation. 180 divided by 6 is 30. 30, 0 is a point on my graph. That's my x-intercept, and that's the point that they have right here. They have 30, 0. There's that point. Let's do the y-intercept this time. Set x equal to 0. So what does that mean? The x term goes away. You're left with 10y equals 180. If I divide both sides by 10, I'll get y equals 18. 18 is the y-intercept, the value of y when x equals 0. They have a point on the graph 0, 18. Use a ruler, draw the line that goes through that right there, and boom, you have a set. Now, in a real world scenario for this, x and y should probably be discrete because it's number of tables. So the fact that we're drawing a line that goes through that being continuous probably isn't accurate. But for the sake of large scale and everything else, I think we're going to be okay with it, especially because we're interpreting the intercepts more than anything else. And if we restrict ourselves to whole numbers, that's fine. Now, they did say interpret your results. What does the result of 30, 0 mean? What does x equals 30 mean? X is the number of small tables. Y equals 0, y number of large tables means you can have, to fit 180 people, you can have all of your tables be small. You can have 30 small tables and 0 large tables and you'll fit 180 people. You could also do 18 large tables and 0 small tables and still fit 180, and anything in between. By that, I mean whole number values. If you have 10 large tables, how many small tables would you need? That kind of stuff. And maybe they ask that. I don't know. But there's a situation. Part B, here it is. Find 4 possible solutions in the context of the problem. Okay, besides the 2 that you found, and remember, solutions are points that are on this line. This is a solution. This is a solution. Let's find 4 others. Substitute values for x, get values out for y, or the other way around. It's up to you because we're out of standard form right now. You can get it in y equals mx plus b form if you want to, but let's see what they do here. They say only, and here's what I said, only whole number values make sense in the context of the problem. That's because tables are integers. Because besides the intercepts, it appears that the line passes through a couple other points. Oh, yeah, we could also use the graph to make the determination. They said it appears to cross through the point 10, 12, and I agree. And 20, 6. And to verify those solutions work, boom, there we have it, 20, 6. Okay, so it looks like they're allowed to use these 2 as solutions, 0, 18, and 30, 0. So that's 4 solutions right there. 10, 12, and 20, 6. So that means we could do 10 small tables, 12 large tables, 20 small tables, 6 large tables, or 30 small tables, 0 large tables, or 0 small tables, 18 large tables. There are probably other combinations. Maybe. I don't know. But based off those combinations there, we will fit 180 people. And they did some double checks, plugging in 10 and 12 into here. They get 180, and 20 and 6 to get 180 as well. All right, guys, that's the lecture portion. I made it longer than it probably should have been. What I think is going to happen, though, is the problem set will become more concise as a result. I'm going to do the problem set based on the notion that you heard the lecture portion a little more so. Let's start with the vocabulary and core concept check, though. How are x and y intercepts alike? How are they different? They're alike in that they are the values of, those variables when the other variable is 0. They are values, let's see, they are points on their respective axes, the x and y axis, and they are the values of themselves when the other variable is 0. You set the other variable equal to 0 and you can solve for it, and you can do that for either set here. Now the graph doesn't have to be in standard form for you to determine x and y intercepts. I want to make sure you know anytime you set y equal to 0, you're going to get an x-intercept and vice versa when you solve. But out of standard form, they're both on that one side of the equation that they're easy to solve for when the other goes away. It's really nice. Number 2, which one doesn't belong? Which point does not belong with the other 3? Explain your reasoning. I'm going to call this one A. I see what is also a y-intercept, value of y when x equals 0. This one's interesting. I'll leave it here for a second, but it's both an x and y-intercept at the same time. X-intercept is the value of x when y equals 0. Y-intercept is the value of y when x equals 0. The x and y-intercepts are both 0. They're both at the origin. When I look at this one, though, this is not an intercept. I'm going to say this is the B, while this is an x-intercept, and this is both x and y-intercepts together. The A's are your intercepts. These are intercepts, both x, y, the other thing. B is just a nothing burger. It's just some other point that's on your graph. So that one's different. All right, guys, we're going to start with the problem set. We have numbers 3 through 38 to do. And I'm going to go ahead and get started. You will need graph paper for this stuff, so whatever you need, go ahead and print it out, pause this thing, and then come back. So let's go ahead and get started. Numbers 3 through 6 graph the linear equation. Notice they didn't call it linear function because if you do know anything about these are horizontal and vertical lines. Horizontal lines are linear functions. Vertical lines are not, but they said graph them. So number 3, we're going to graph the line x equals 4. X equals 4 is the equation of the vertical line that crosses through the x-axis at x equals 4 and every other point where x equals 4. This is 4, 1, 4, 2, 4, 3, 4, 4, 4, -1, -2, -3, -4. And as a continuous relation, not function, as a continuous line, we will connect the dots or just draw straight up vertical line that goes through there. This is the line x equals 4. Yes, it is vertical because we go right 4 units to draw the line. Again, I'm going to do this more out of what we said in the lecture, and I said a lot about these in the lecture, so I'm not going to get deep into it. We only have 4 of these ones to do. Y equals 2. Y equals 2, number 4. This is a horizontal line because this crosses the y-axis at y equals 2, and here's 1, 2, 2, 2, 3, 2, 4, 2, -1, 2, -2, 2, etc. What do they all have in common? The y value is 2. It's a horizontal line, goes across here. It is a function. Don't know if that matters, but it is a function. Draw arrows on your lines, by the way, and there we have it. Numbers 5 and 6, I'm going to go very fast. I'm not even going to really explain them, but y equals -3 is a horizontal line that crosses -3 for y, etc. So what most people tend to do is they plot the intercept first, and since we're talking about intercepts so much in this section, I might as well. So I will plot at y equals -3, sure, but I need to draw a line that goes through there. In this case, it'll be horizontal, not vertical. What tends to be a mistake, and I don't know if it's going to be part of the error analysis, but what tends to be a mistake is people will do this. They'll draw the point y is -3 right there, and then they'll draw a vertical line like this, as if that's any different than the line y equals 7 and drawing a line through this right here. Guys, those are literally the same thing. Somehow I think that's not the answer. The answer would be right here, this horizontal line. Number 6, x equals -1. X equals -1 is a vertical line that crosses through -1 on x among all the other x values that are -1. But I'm going to plot -1, draw the vertical line. Now, if only every problem was this easy in the whole section, we'd be great. But I hope that as life goes on, and as we do other sections for these, you don't forget how to draw horizontal and vertical lines or what their equations look like, because they will be used in the future. In exercises 7 through 12, find the x and y intercepts of the graph of the linear equation. They did not ask us to graph. We're just finding the intercepts. So after that, we're going to be graphing based off that. Number 7 says 2x plus 3y equals 12. Okay, the idea is this. X-intercepts are values of x when y equals 0. Y-intercepts are values of y when x equals 0. For the x-intercept, set y equal to 0. So the equation will look like 2x plus 3 times 0 equals 12. And this is the only problem that I'm going to be doing it in this variety, which is 2x plus 0 equals 12, which is 2x equals 12. If you notice what happened when y equaled 0, the term went away. I just have 2x equals 12. That's as simple as it gets. Now, you don't want to cross it out because we're going to use it, the y thing, later. You can put your finger on it, cover the y, and say, what does the equation say now? In this case, it says 2x equals 12, right? If I divide both sides by 2, we get x equals 6. That means the x-intercept is at x equals 6. I don't know if they want it as an ordered pair. Sometimes people say x-intercept is 6 is correct, or x-intercept is 6, 0. I'm probably going to be writing the ordered pair to remind you what the point is. Let me check and see what they did for their, hold on, I'm trying to go to the other sets. I want to see what the they say on these things to be sure. X equals 4, solve for x, The x-intercept is 4. Okay, we'll just use the whole numbers, but this is the point where it exists on when we do things like that, okay? So on these scenarios here, like this one on number 7, x equals, the x-intercept is 6. Okay, x equals 6. We'll do it like that. Y-intercept, very little room to write over there now. The y-intercept, we set x equal to 0. Consider this equation, 2x plus 3y equals 12. We'll now say 2 times 0 plus 3y equals 12. That means 0 plus 3y equals 12. And as you can tell, that means the x term goes away. 0 plus 3y is just 3y. So we can divide both sides by 3 there, and we get y equals 4, which means those are our x-intercepts and y-intercepts. 6 is the x-intercept, 4 is the y-intercept. I feel compelled to still write that that means there's a point on the graph that's 6, 0, and there's a point on the graph that's 0, 4. As a math teacher, I'm very bad syntactically with understanding whether I can write x-intercepts as this or just the number itself. But the x-intercept is 6 and the y-intercept is 4. These are where they cross. Okay, number 8 says 3x plus 6y equals 24. This is where you're going to start seeing me be a little more expeditious. To find the x-intercept, I set y equal to 0. When I set y equal to 0, the term goes away. The equation now says 3x equals 24, and divide both sides by 3, you get x equals 8. The x-intercept of this is 8. It crosses at the point 8, 0. The y-intercept, you set x equal to 0. And what happens? Your equation says 6y equals 24. That's a y, by the way. You divide both sides by 6, and you get y equals 4. The y-intercept is 4. That means it hits a point that's 0, 4. That's all we're doing, guys. That's it. I mean, we'll graph these later, but that's how you find them. That's why standard form is so great to graph out of, because it's the quickest. There are 2 calculations we had to do. We had to divide by 3 and divide by 6. Did we have to multiply by 0 and add with 0? I guess if you want to argue it that way, sure. But if you understand the whole magic step of, hey, it went away, I'm good with that as well. X-intercept in this case here, the y value becomes 0. The term goes away. What does your equation say? Negative 4x is negative 16. When you divide both sides by negative 4, we get x equals positive 4. There's an x-intercept of 4, 0. Or, sorry, of 4. The point is 4, 0. The y-intercept, set x equal to 0. Don't mind if I do. Whoa, hide it. It's gone. Where is it? Where is it? I don't see it. Do you see it? Where'd it go? Where'd it go? Where'd it go? It's gone. The value of y when x equals 0 is negative 2. Our first negative y-intercept. Congratulations. 0, negative 2 is where that one crosses. Number 10. Do I have to cross them out anymore? I will cross it out on number 11 again. You'll see why in just a moment. But negative 6x plus 9y equals negative 18. Let's try without crossing out here. X-intercept, set y equal to 0. Do me a favor. Put your finger on 9y if you want to and hide it. I'm not crossing it out. Tell me what your equation now looks like when y is 0, when the term goes away. Negative 6x equals negative 18. It's the thing without the y in it. So divide by negative 6, and it's x equals positive 3. That's the point 3, 0. The y-intercept, take your finger, hide negative 6x. Put your finger on it. It's gone. It's gone. My equation says 9y equals negative 18. Divide both sides by 9, you get y equals negative 2. The point on the graph is 0, negative 2. X was 0. Now, number 11, I'm going to go back to the crossing out method because a mistake could be made right here if you do the finger hiding thing or try and go invisible, whatever. I want to make sure to avoid what I find to be a common mistake. And this is true in a lot of different ways. And by the way, these answers aren't going to be pretty, but it doesn't mean that they're still not that things. Okay, the x-intercept, I'm going to once again set y equal to 0. Now, right, we can do this thing right here, right? It goes away, and we get 3x equals 2. Now we divide both sides by 3. Not a perfect number. This is 2/3. That's just what it is. 2/3. 2/3 of the way up from 0 to 1. That's 2/3. Or sorry, 2/3 of the way right to 1. because it's an x-intercept. So 2/3 comma 0. Now the y-intercept, we set x equal to 0. Now, whether you did the finger covering thing, I'd try it. Try and cover your finger on the x value. Tell me what your equation looks like. Because here's what a lot of people are going to say. 6y equals 2. Is that right? No. This is my own form of error analysis, and I want to stress it right now. What's wrong? I'm going to do something on my cross out here. I'm going to move it a little bit to the left. What's wrong? It's negative 6y. 3 times 0 is 0. 0 minus 6y is negative 6y. Do not forget that negative there. So whether you're doing the hiding form, whether you're just ignoring your signs or whatever, it's the y term that tends to be ignored and forgotten. You're not going to mess up on the x term right here, calling this one negative when this one goes away. You're going to remember the negative there. People are going to forget the negative here, especially if you cross it out, cover it, whatever it is. It happens all the time, right? We've done previous equations where if I had to subtract 3x from both sides and you cross this thing out, people will write 6y equals. You'll forget the negative there. Much less when we do it right here. Absolutely, it will be forgotten. So be very, very careful on that. Anyway, we divide both sides by negative 6, and that's obviously the big change on this. And this reduces to negative 1/3. And that's how we can write that one. So this is y-intercept of 0, negative 1/3, like so. Okay, number 12. Negative x plus 8y equals 4. So it doesn't have the same confusion with the negative y kind of thing, but x is negative. No crossouts, no nothing. Let's see how we do on this one. The x-intercept, y equals 0. We have negative x equals 4 as an equation. We're not done. We have to solve for x. Divide by negative 1, switch signs, whatever you need. X is negative 4. Got an x-intercept of negative 4. There's our point we cross. The y-intercept, we have 8y equals 4. Negative 0 is still 0, and that plus 8y is still 8y. Divide by 8. 4/8. Don't go to the calculator. Don't say 0.5. We got a little 1/2 on our hands as reduced. And it's like that. Okay? So that's what these look like when it comes to the form. These points are points that we can plot on our graph so easily. And if we have a ruler, we can draw a line through these so well. And we're about to do those. 13 to 22, next 10 problems. Get out your graph paper. Use intercepts to graph the linear equation. Label the points corresponding to the intercepts. So, number 13 says 5x plus 3y equals 30. We are going to sketch a graph, but in order to do it, let's find them intercepts. So I'm going to place the graph paper here to see what kind of room I need on these, and I'm going to fit all the room on this side here. So my x-intercept, set y equal to 0. I got 5x equals 30. Divide both sides by 5. I'm going to say that out loud here, and we get x equals 6. You know, I'm going to let you know right now, guys, in the future, I'm going to start doing more of that. Less showing of action of the divide by 5 and more of just making that happen. Future things, that's going to happen more so, especially once we hit like chapter 5. That's all I'm going to do. I'll say it, divide both sides by 5, but I won't write it. Right here, I feel like just this simple division is something that we can get away with not doing the action of. The book's not doing it. The book, sometimes the book doesn't do it quite often. I think it's at a point that they say, we really got to know that for ourselves. Anyway, the y-intercept, you set x equal to 0. We get 3y equals 30. If I divide both sides by 3, I get y equals 10. Now, we've talked about what these points are when we draw them. The x-intercept of 6 means there's a point on the graph that's 6, 0, right here. The y-intercept is the value of y when x equals 0. That's 0, 10, like this. There's the y-intercept. And we can draw a line through these 2 points. This is where you use a ruler. Use a ruler, draw a line through those 2 points. Fit it within the entire window range, though, please, because what the idea is there are multiple ways we could graph this. In standard form is one of them. We're doing it with the understanding that we're going to strike through the entire window range as far as we can. That's the way to do it. Otherwise, we'd use a different form, plot as many points as we could, and go about it that way. So there's the graph of this guy, number 13. Number 14, we have 4x plus 6y equals 12. And we're going to find the x-intercept and y-intercept. Our equation when y is 0 says 4x equals 12, and we can divide both sides by 4. 12 divided by 4 is 3. There's a point on our graph that's 3, 0, like this. I don't want to label yet because I don't know where the line's going to go. I'll know more when I do the y-intercept. The y-intercept, That's 6y equals 12 when x is 0. Divide by 6. 12 divided by 6 is 2. Y equals 2. So it's right here. Now I can know more. The line's going to go this way. So my labeling, I'll probably do like this, 3, 0. I think they asked us to label. So 0, 2. Now this is one of those things, again, use a ruler to draw through here, but you don't just draw it like this, right? You have to extend it out. I might have to start that way because now I can use my tool and do my best stretch based off that. It's probably going to look something like that for me here. Draw arrows, right? My line tool has arrows on them, but draw arrows on each one you do. Number 15, negative 12x plus 3y equals 24. The x-intercept setting y equal to 0 leaves you with the equation of negative 12x equals 24. You divide both sides by negative 12. This is where one of those actions, you got to be careful if I'm not writing the in between. 24 divided by 12 is 2, but positive divided by negative is a negative. So I got that point there. And the y-intercept, that's a positive 3y when x is 0. 3y equals 24, and we divide both sides by 3. Whoops. We generally haven't been writing that anymore. But y equals 8. Not anymore, but in these quick division problems, I'm kind of on them. And like I said, someday they'll be completely removed, and you will have to be okay with it. So there are the points, 0, 8, and negative 2, 0. Draw that line, though. Get it going. And again, if you have a ruler, you get to preview the ruler. That's like, I play guitar. I don't play piano. I've played piano before, but the thing I like about guitar is I can put my finger on the strings and I don't need to make a sound yet until I pluck it, which means I can make a mistake on placing it or kind of get comfortable with it, figuring it out before I have to play it. For piano, yeah, I guess you could lay your fingers over it, but the idea is once if you're doing something whip fast on here, I can place these before I play. On piano, I'm kind of just going and playing, and I don't know if that's true. Maybe that's not the way you're supposed to do piano. Maybe it's supposed to be by feel, get the feel beforehand. The point I was going to make is that with a ruler, you can place the ruler on the paper without actually drawing the line. So you can figure out where it is in the ruler. With my line tool, I got to draw the line straight up. And if I make a mistake, the mistake's made. Anyway, so x-intercept. Okay, I'm going to do this for this problem and this problem only. Mentally, negative 2x equals 18 is the equation. So divide by negative 2, it's x is negative 9. And the y-intercept, this says 6y equals 18 now. Divide by 6, and that's y equals 3. So those are the intercepts of negative 9 and 3. Reason why I'm doing it on this problem is because it seems like my next questions are going to have fractions, decimals, things like that. So I wanted to do this for one of them and just express how quick it is that you can make a graph out of 2 points. Because that's the point of this, right? I need 2 points to make a line, a unique line. And that's exactly what's happening here. I got negative 9, 0 and 0, 3, which I still have to label. But that's how quick it can go from that equation alone. That's just how fast we can make it. So negative 9, 0, 0, 3. And as you saw, kind of the line kept messing up there. I still want to fix it a little bit more. Okay. Now the next questions here seem to hit some form of fractions, and it seems like all of them do. This is one of the, I'm not going to say downfalls of standard form. Sometimes when you have a fraction, there's nothing you can do about it. A fraction's going to be a fraction, and that's just how the graph rolls. Sometimes when we use y equals mx plus b form, there's a preference in making it so, despite the fractions that exist. But on these ones here, we're going to graph with fractions involved, okay? So with this one here on number 17, we have, for example, on the x-intercept, I'm going back to some, you know what? I'm going to write this out when I feel like I need to, like on x-intercept. I got to divide, I'm even going to write this part, dividing by negative 4. Negative over negative is positive, and 30 divided by 4, you can divide them by 2, and it reduces to 15 over 2. Now, you might be curious as to what that actual value is as a decimal so that you can plot it properly. That's 7.5. So 7.5 is our x value, or 7.5. The y-intercept is a little bit easier this time. I think I can do this mentally. Understand that the number that's in front of y is what you're going to be dividing negative 30 by. So when x is 0, I'm going to divide negative 30 by 3, and I get negative 10. So that one was a little more mentally accomplishable. Y is negative 10 is way down here for the y-intercept. The x-intercept is at 7.5. right there. And that's exactly 7.5. 2 points still make a line, and that is still your graph. There's no fighting the decimal. That is the graph in and of itself. So again, when it's a decimal or fraction answer of some sort, guys, I'm going to be writing out some of the work. When it's an obvious integer answer, I'm just going to do it mentally. I hope that's okay. Number 18. It gets you more into the skill and mindset of what you're doing on the problems. And I can verbalize it. Number 18 is another one where it looks like the x's. I mean, tell yourself right now, right? How am I coming up with, oh, that's going to be a decimal, or oh, that's not going to. Take a look at the coefficient in front of x and ask yourself, can I divide it by 21? Positive or negative? Can I divide it by 21? Not really, not evenly. So for the x-intercept, let's write the equation. Negative 2x equals negative 21. We'll divide both sides by negative 2. There's also a little trick in negative over negative is positive. And that's 21 over 2. 21 over 2 is 10.5. This one gets a little bit out of reach on my graph, right? A little bit. We'll deal. We'll deal. Halfway away from 10 is fine. Y-intercept, a lot easier. 7y equals negative 21. Divide negative 21 by 7. You get negative 3. So x-intercept is there. Y-intercept is there. 10.5. Here's 10. Maybe that's 11. 10.5, just halfway over. It's fine. We're fine. It's all good. Negative 3. 0, negative 3 is our y-intercept. And 10.5 comes 0 is our x-intercept. So from here, I can go in this direction and I'll fix it. Don't worry, Captain. We'll buff out those scratches. Extra credit if you know what show that's from. Or what episode it's from. And I'm not impersonating the character's voice. But don't worry, Captain. We'll buff out those scratches. All right. Number 19. Number 19 says negative x plus 2y equals 7. Now, this is one where, there's no fraction on the x-intercept, you can probably tell, but you still have to be careful for this one. This is negative x equals 7. That doesn't mean the x-intercept's 7. It actually means it's negative 7, right? Divide both sides by negative 1, something like that. Switch the signs. So I'm still writing that one out. This y-intercept will be a fraction. We got to divide 7 by 2. So what'll that get you? 7 over 2? 3.5, right? 3.5. So that's the x-intercept. That's your y-intercept. Let's get them p-lotted. Let's get them l-abled. 0, 3.5 and negative 7, 0. And let's get the L line going. Like that. All right. Now, by the way, when I say use a ruler, let me rephrase that. Use a straight edge. A ruler is not only for drawing straight lines, but a ruler can also be used for measuring distances of things. We don't need to measure distances. You just need a straight edge. You can use an ID card. Driver's license, library card, whatever, credit card. You can use the edge of a piece of paper. You can use, I don't know what I have on here, this Saw the Final Chapter Blu-ray thing. I had to use that for something a bit ago. Right? You can use different things like that as long as you can draw something straight on it and preview it. Okay. Let's write these ones out this time. X-intercept 3x equals negative 5. Divide by 3. That's negative 5 over 3. Now, as a decimal, that one gets a little weird. It's not an exact number. We'll still plot the point as if it's rounded. This is around negative 1.67, right? It's kind of a weirder number to talk about as a whole. Your calculator will say negative 1.666. It's negative 1 2/3. Right, it's a mixed number, which we generally don't talk in terms of mixed numbers. Now, the y-intercept, this is one of those be careful moments. You said x equal to 0. This actually says negative y equals negative 5, not positive y. Therefore, positive y is positive 5. And it's like that. Not a fraction, but just one to be careful of how that sign changes, especially because it was the y value, the one that we actually often make a mistake on when it comes to recognizing the negative that's in front of it. For whatever reason, it's just ignored. And I state that as if I thought I had found the cure to it a long time ago when teaching by stating don't forget it, and people still forget it. It's the strangest thing is through my decade plus of teaching. I know the common mistakes students make. And it's quite interesting to know that there are common mistakes. And when I say common, I don't mean, it's a little sparse. It's like the majority. It's like the super majority, that when they make the mistake, that's the one that it'll be. And that being said, I now mention that maybe it's a thing where, like, I'm performing inception. I'm planting the seed that says, now that I've exposed it to you, that now it's a mistake you will make because you've seen it. But I try and state it in a preventative way, as if saying, people are going to make this mistake, don't make it. And maybe I'm saving some people from making it, but there are still so many people that make whatever. I'm not talking about just that mistake. I just mean in general, the common math mistakes that you'll ever hear me call out are the kinds that are like, I caution you about it. I say, don't do this. Here's why and here's whatever. Yet it still happens. So I don't know what's going to do to fix it. I think we just have to practice. We have to be careful. Now the x-intercept here, I'm going to have to multiply both sides by -2/5. And I clearly didn't give myself enough room to write that. But that's what makes these go away, gets x by itself. Now, -2/5 times 10. 10 divides by 5 to become 2. 2 times -2 is -4. So there's our x-intercept. Hey, it's a whole number. Now, the y-intercept is really easy. Turn that x term into 0. Y is 10. Y equals 10. That's your y-intercept right there. Now, sorry if I didn't label on the previous problem. I was too busy talking. I'll make sure to label on this one. So this is -4, 0. And 0, 10. And it's good that we keep highlighting. I like that they're asking us to label, because we have to remind ourselves of what those other values were. Look, these terms aren't just going away. I'm turning x into 0, right? It's not going away. So the x value is 0 there, and that's the ordered pair. And we have to keep reminding ourselves of that for intercepts in the future. Number 22. Last one to graph in this stage. And remember, we're only going to number 38, so we are more than halfway done. I mean, granted, I don't know how the word problem things are going to work out. Probably error analysis comes up later. Pretty quick there. But with this one here, we have an x-intercept of... What do we got to multiply by here? Because this is division, right? We have to multiply this by -2 times -2 over -2 is 1. And then -4 times -2 is 8. We got an x-intercept of 8. The y-intercept is like the last one. It's not the same number, but set x equal to 0, its y is -4. So the y-intercept's -4. X-intercept is +8. Our graph goes this way. With this line. Okay. Make sure you're still drawing your arrows. Okay. That's 10 different graphs. Hopefully standard form's making a lot of sense, even with decimals and what we do on them. Not too bad, right? Pretty quick graphs. I enjoy them. Number 23. But, right, we didn't use a table. And even though we plugged in 0, 0 is such a special number as far as how things disappear. It's really easy. Number 23, modeling with mathematics. A football team has an away game, but the bus breaks down, and the bus breaks down. The coaches decide to drive the players to the game in cars and vans with parental consent. 4 players can ride in each car. 6 players can ride in each van. And they're making the equation. There are 48 players on the team. The equation 4x plus 6y equals 48 models this situation where x is the number of cars and y is the number of vans. So x is cars, y is vans. Remember that, because we probably have to interpret this situation here in a bit. Graph the equation, interpret the intercepts. So as far as this goes, we've done x-intercepts and stuff before. Maybe we can do these ones mentally, y'all. X-intercept. Actually, here, before we talk about that, let's interpret the equation as a whole. 4 people per car times the number of cars is the number of players that go in all the cars. 6 players per van times the number of vans equals the number of players that go in all vans. 48 players total. Okay, x-intercepts. Set y equal to 0. 4x equals 48. Actually, I'll at least write that. Divide by 4, you get x equals 12. Y-intercept. 6y equals 48. Set x equal to 0. Divide by 6, y equals 8. So these are our intercepts, 12 and 8. We have to interpret these. Interpret these means provide context for the situation that we're talking about. Remember, it's not just 12, it was 12, 0. Right? 12, 0 means the player you can drive 12 cars and 0 vans to fit all 48 players. Vans. That is a possible solution to this. Not just solution, you know, like when I think solution, or sorry, when I say solution, I'm thinking mathematically. When I say the word solution, I'm thinking of like a point on the graph. But it's also a solution to the problem, right? This is a bus broken down problem. Hey guys, I have a solution. Why don't we drive 12 cars? Yeah, that's it, right? Another solution. Hey guys, I have a solution. I have 8 vans and we can fit 6 people per van. So you can drive 8 vans and 0 cars and still accommodate all 48 players. Are those the only options? No, but that's the interpretation of the intercepts. Those are the extreme ends of what if you had no cars to drive? What if you had no vans to drive? Could you still fit all 48 and what does it look like? So let's go to the graph of this as well. I need to make one of those. These graphs are first quadrant only, right? Only positive things matter for us here, so I can like make it a little bit bigger here. Now we have to go to x equals 12 and x-intercept there. That's a little bit out of reach. I am going to force fit it. That means this is 10 and out here we can kind of make our own 11 and 12. So I am force fitting the x-intercept. There it is, 12 comma 0. 12 cars, 0 vans, or 0 cars, 8 vans. Now, this is not, like I said, this is a first quadrant graph only. This does not include negative values. And I mentioned this in the lecture portion as well. This is a little bit off kilter when we draw a line because a line generally implies continuous. This is not continuous because you can't drive a fraction of a car. But what this allows us to do is use the graph, and if you got a ruler, then you're possibly crossing through other integer values for which we can find other solutions. And that's actually what they want us to do. Part B, find 4 possible solutions in the context of the problem. So I actually already have 2 solutions. 2 solutions that I have are 0, 8 and 12, 0. Because technically, we didn't interpret those parts in part A. We interpreted them, but we didn't actually determine them as solutions. So on part B, 12, 0 is one solution. 0, 8 is another solution. And remember, we already interpreted these. Now, in the context of the problem, there are 2 others. You can, on the graph, if you have this drawn correctly, and if they made a good problem with it, find 2 other points as integers that they cross through to fit exactly 48. I'm seeing these ones. I'm also seeing this one right here. So let me call these points out. This is 3, 6, and I'll tell you what, these probably aren't approximate. We can double check. They should work. This is 6, 4, and this is 9, 2. Now, what we're stating on each of these 3 sets, besides the 0, 8, and the 12, 0, so I found 5 of them, and I'll just go ahead and type some things out with that, is these are different ways we can fit all 48 people with whole number cars and vans, right? You can fit 48 players using, in addition to the intercepts, we have these 3 new solutions here. One of them is, let's bullet point this thing, 3 cars and 6 vans, or cans, 6 cars and 4 vans, 9 cars and 2 vans. Now this is one we should be double checking. I'm only going to double check one of them physically. The other ones I'll do mentally with you. Let's try the 3 cars and 6 vans. That was 4 people per car, 4 players per car times 3 cars, plus 6 players per van times 6 vans. Let's see if that equals 48. That's 12 plus 36, and that is indeed 48. So 48 equals 48. That one does definitely check itself. Let's try 6 cars and 4 vans. That's 24 players plus 6 times 4 is 24. 24 plus 44 is 48 as well. That works. 9 cars is 4 times 9, which is 36 players in the cars. 2 vans is 12. 6 times 2 is 12 players in the 2 vans, and 36 plus 12 is also 48. So those all check out. These were the other 2 solutions right there, and there we have our set. Those might be the only solutions that are possible for that as well when it comes to integer amounts. And getting exactly 48. No space left over. Not like, oh, I'm just going to put 5 people in this van, not 6. No, we're maximizing our opportunity there. Or minimizing the number of vehicles, whatever. Number 24, probably same kind of thing. You're ordering shirts for the math club at your school. Short sleeve shirts cost $10 each. Long sleeve shirts cost $12 each. You have a budget of $300 for the shirts, and they give you an equation, 10x plus 12y equals 300. This models the total cost where x is number of short sleeve shirts, y is number of long sleeve shirts. Everything's the same here. $10 per shirt times number of short shirts, short sleeve. $12 per long sleeve times number of long sleeve. And then both these are dollar amounts. This is how much money you spend on all short sleeve, on all long sleeve, and in total. So money plus money equals money. And that's how the equation works out. So remember, they're writing the equation for you. Maybe at some point we have to write our own, and we have to know how to do that. Graph using intercepts. X-intercept. Set y equal to 0. 10x equals 300. Divide 300 by 10. You get x equals 30. Y-intercept. 12y equals 300. Divide by 12. Y equals... I don't know if that's a whole number. 300... It has to, right? No, it doesn't. It's the... Yeah, yes, it does have to be. 25. I don't know why I had trouble with that one. 25. Okay. If we graph this one, we clearly have to do a scale change on our x and y axes. And this is one where, you know, I want to find more integer values where I can, but given my scale, it's kind of I might have to go by 5s, which shrinks the ability of what we can see, but I might have to go by 5s. That means this will be 50 and 25. And same thing here, 25 and 50. Again, nothing on this end matters for me here. No. But those are our intercepts. X-intercept here, and this is 30, right? 5, 10, 15, 20, 25, 30. So 30 comma 0. And they did say graph, right? Graph the equation, interpret the intercepts. And this is 25, 0 comma 25. So we have this whole math club dealio. Oh, this is going to be tough to tell. This is going to be tough to tell, guys. I have to thin out this line a little bit just to see when it looks like we're actually hitting other points. Oh, I can't tell on this one. Okay. Anyway, what was I going to say? Interpret the results. So with this thing here, we have a budget of $300. We could buy all short sleeve shirts, and we could buy up to 30 of them. No long sleeve. Or we could buy all long sleeve shirts and buy 25 without any short sleeve shirts there. So that's what the intercepts are interpreting. It's not saying we have to. I'm just saying those are options. It's kind of the more if scenario. If you bought all short sleeve shirts, you could budget for 30 of them. If all long sleeve, you could budget for 25 of them. All long sleeve means no short sleeve, etc. That's where the zeros come from on the other side. So that's my interpretation of part A. Part B, 12 students decide they want short sleeve shirts. How many long sleeve shirts can you order? I like that they said that instead of find 4 possible solutions, because with my scale, I'm not hitting any of those other integer values. You have to keep in mind, though, these are by increments of 5, multiples of 5. So that means there could land on other ones, like X could be, 18 and Y could be whatever. And that would be a totally different scenario. So here they say 12 students decide they want short sleeve shirts. So for part B, we're going to say it when X equals 12. So our equation, 10x plus 12y equals 300. We're going to do 10 times 12 plus 12y equals 300. So we're going to find out if we do 12 short sleeve shirts, that's going to cost $120. So that means, because I'm going to express every part of this, that means we can buy this, we can spend this amount here on it. How much is that? Subtract 120. That means in long sleeve shirts, we can spend $180 on long sleeve shirts. If they cost $12 each, then that means that each individual, that means that you could afford, come on, Mr. Robinson, 15 long sleeve shirts. Why am I having so much trouble with that? Sleeved shirts. Before I think I just said sleeve. Long sleeved. Okay. All right, that's part B. Okay, we have error analysis on numbers 25 and 26. Describe and correct the error in finding the intercepts of the graph of the equation. Of the. So we're not graphing. Now, they found an x-intercept by setting y equal to 0, and they solved correctly. They got x equals 8. Look at the math. It actually pans out. And the y-intercept, they set x equal to 0. Boom. And then they solved this equation. They got y equals 2. That's all good. They said the intercept is at 8, 2. Okay. Lot wrong with that. The math is right. The conclusion is wrong. They do that quite often. The math is correct with but the conclusion on intercept or intercepts is incorrect. First of all, intercepts occur on axes, x or y, which means one of the values must be 0. One of the coordinates must be 0. Secondly, there should be 2 intercepts. One for x and one for y. So we got the right numbers, but we set y equal to 0, right? Again, I may cross it out and say I ignore it, it goes away, all that kind of stuff. But don't forget what y was. When y equals 0, x equals 8. What that means is there is an x-intercept of 8, 0. Or there's a point that's 8, 0. And when you plot it on the graph, you say, that's the x-axis. That must be the x-intercept. So whatever way you need to remember how that works is what it is. Now, you can say, let's see, in finding the intercepts, you could say the intercept is 8, right? Because they kind of said that before, but the point that it exists on is 8, 0, not 8, 2. That is not an intercept. That is not on an axis. The y-intercept would be 0, 2. You substitute 0 for x, you got 2 for y, and that's the point there. Just like this one, right? We substituted 12 for x. What do we get for y? 15. That means there's a point on this graph. That's 5, 10, 12, 15 right there. There's my 12, 15. That's a solution, but also that's a point on the graph. Not an intercept, but it's a solution. When I substituted 12 for x, that's what I got for y. It's not that y equals 15. It's y equals 15 when x equals 12. And it's a very specific point. And that's the same thing for intercepts, that it's when x equals 0, y equals 2. When y equals 0, x equals 8. Like that. So I'm yelling at you, person who did this problem wrong. Why? I'm correcting your errors all the time here. Okay. Let's see what they did on number 26 so wrongly. Substitute 0 for y for the x-intercept. They got 5. Substitute 0 for x for the y-intercept. They got 2. Math is all good. Their problem here is, okay, now listen. Now, first of all, they did write these as ordered pairs. I wasn't certain if they could write them as ordered pairs or not. I literally don't know. But it looks like they did that, and that's not the error. The error is they have the x-intercept as a y-intercept and the y-intercept as an x-intercept. Swap the coordinates. X-intercept is on x-axis. And when y equals 0. Literally, we substituted 0 for y. Or maybe they don't know this. Ordered pairs, let's see, and vice versa. Ordered pairs are represented as x, y. So I don't know which part they messed up. Maybe they're like, oh, shoot, I thought you wrote the y value first. Maybe that's all. Like if I said, hey, plot 0, 5, and then they actually plot it on the x-axis, clearly their x, y coordinates are just messed up. But the x-intercept is at, the number is right, it's in the wrong spot, 5, 0, and the y-intercept is 0, 2. So again, they're doing the right math. All's good there. I wish they did one where there was a negative and they ignored the negative on the problem, but they don't know. They can't anticipate that kind of student mistake. Okay, number 27, making an argument. You overhear your friend, you're eavesdropping. You overhear your friend explaining how to find intercepts to a classmate. Your friend says, when you want to find the x-intercept, just substitute 0 for x and continue to solve the equation. Is your friend's explanation correct? Explain. Incorrect. Your friend is incorrect. My friend is incorrect. They need to set y equal to 0. The x-intercept is the value of x when y equals 0, not when x equals 0. Our goal is to solve for x in an x-intercept. Duh. So yeah, with friends set y equal to 0, you got to correct that at once because peers can't give false information to each other, right? That's not helping. We want people to help each other. We want them to help each other correctly. Number 28, analyzing relationships. You lose track of how many 2-point baskets and 3-point baskets a team makes in a basketball game. The team misses all the 1-point baskets, like free throws, and still scores 54 points. They're doing that so they can keep this at a 2-variable case, right? They have to do that. Still scores 54 points. The equation 2x plus 3y equals 54. See, I want to come up with these. Models the total points scored where x is the number of 2-point baskets made and y is the number of 3-point baskets made. It says find and interpret the intercepts. They didn't say graph. They said find and interpret the intercepts. So A, x-intercept. I'm going to do this mentally. We've done this a couple times now. 2x equals 54. We got to divide 54 by 2. We get 27. That does mean 27 comma 0. I feel like I can now write that because the book did. The y-intercept, you said x equal to 0. You divide 54 by 3 and you get 18. When x is 0, y is 18. Now we have to interpret these. There's a possibility because you lost track. Maybe you weren't watching the game at all. You said, hey, scored 54 points. No free throws were made. How could have they scored? One possibility among many others, but one possibility is that you scored, or the team scored 27 2-point shots, shorts, or baskets, and 0 3-point baskets. I'm going to write the word for 2 and 3. Otherwise, that looks really weird to have those right next to each other. And 0 3-point baskets. That is one of the things that happens interpretively. The other alternative to this is this. The team scored 0 2-point baskets and 18 3-point baskets. Those are the intercepts. Remember, there are other possible solutions, but those are. Part B. Can the number of 3-point baskets made be odd? Explain your reasoning. B. Can it be odd? That's a great question. Here's the thing. 3 is already an odd number. What happens when you multiply an odd by an odd? You get an odd number out. The problem with that is the number of points scored was even. So the difference between an odd and even is an odd, which means your 2-point total would have become an odd number, and that's just not possible. So that's a great question. No. There cannot be an odd number of 3-point baskets scored. That means there's no solution where it's maybe they scored 9 3-pointers. No, that's not possible because that wouldn't add to 54 anymore. No. No, because your 3-point, let's see, odd, I don't know. I mean, I said it. If you scored an odd number of 3-point baskets, then the difference between your points total and 3-point total would be an odd amount, which is not possible to total to for your 2-point basket total. 2-point baskets total. Right? Imagine if you scored, like I said, 9 3-pointers. That'd be 27 points. 54 minus 27 is 27. So that means the rest of your 2-point baskets was 27 points. You can't do that. You can't score half a bucket, right? So half a basket. So we didn't score any free throws. So there's that. Okay, part C, graph the equation, find 2 more possible solutions in the context of the problem. So we are going to sketch the graph. These are crazier intercepts, but listen, I can go by multiples of 3 and fit these okay, and hopefully we find other points along the way that are just as friendly. So I don't need any other quadrants other than the first quadrant here. If I go by multiples of 3, this is 30, this is 15, and same thing here. 0, 18 and 27, 0 are among them. Wait, 0, 18. 0, 18. These are going by 3s. So 3, 6, 9, 12, 15, 18. And there was also 27, 0. 15, 18, 21, 24, 27 right here. Okay, those are the intercepts. Let's draw a line. I'm going to keep this one thin because I want to see if this hits another set here. Now remember, if it hits some crosshairs, these are going by multiples of 3. So ones that look pretty decent that I figure are probably working and we'll use them is this one and this one. I can't really see any others, but this one here, maybe these are not the only solutions because remember, these go by multiples of 3. This one is 18, 6, and this one is 9, comma 12. Now on the 9, you're like, but Mr. Robinson, you said you can't score 9 3-pointers. These are 2-pointers. X's are 2-pointers. These are 3-pointers. Says find 2 more possible solutions. Okay, so I found 2 more ones. So to total 54 points, you could have scored 2 possible outcomes. 2 possible scenarios are sorry, I'm trying to format this right. Score 9 2-pointers and 12 3-pointers, or score 18 2-pointers and 6 3-pointers. Let's mentally check those ones out, see if that works. 9 2-pointers is 18 points. 12 3-pointers is 36 points. 18 plus 36 is 54. 18 2-pointers is 36 points. 6 3-pointers is 18 points. 36 plus 18 is 54. So those work. Part C. Okay. Numbers 29 to 32 match the equation with its graph. Now notice that these have the same numbers here for the X's and Y's and stuff like that. I'm going to be very, very minimalistic on these things. We can talk intercepts all day, stuff like that. I'm going to write them out that way. What we could also talk about is just their signs. Listen, the x-intercept each time is either a positive 6 or negative 6, and clearly it's reflected on these graphs. Notice that the scales go by 2s, but positive 6 or negative 6 on those. So honestly, the only thing I care about is not even the division. The x-intercept's either positive or negative. Listen, it's either 6 or negative 6. I'm dividing positive by positive. That'll be a positive there for x. That means it's either this one or this one. The y-intercept is also positive, and it's either 10 or negative 10, right? This one's going to be positive 10, so it looks like that's the y-intercept. I think number 29 is A. They're not asking me to explain, and I've done a lot of calculations with it already. Clearly, I can do the calculations, but the only thing I care about now is when dividing. Am I doing positive over positive, negative over negative, negative over positive, positive over negative? What is the sign of each of them? So let's try this out. Number 30. I divide a negative by positive, I get negative. Negative by positive, I get negative. Both x and y-intercepts are negative. Which graph has 2 negative intercepts? This one right here, C. Number 30 is going to be C. 5x plus 3y equals negative 30c. If this is just a matching game, there it is. Number 31, the constant 30 is positive. Divide it by positive here, I get positive. So positive x-intercept. But this time the y-intercept will be negative because I divide positive by negative. So that'll be D. So 5x minus 3y equals 30 is D. That just leaves B with the last one. Let's see if that works out. Where, oh, I'm sorry, I didn't move this thing over. On number 32, I divide negative by positive to get a negative x-intercept and negative by negative to get a positive y-intercept. That must be this one right here. Negative x, positive y, that is B. So 5x minus 3y equals negative 30 in B. And again, the intercepts were the same absolute value. It was always a 6 or always a 10 for the y's. The question was the signs. Negatives, positives, et al. Okay, number 33, mathematical connections. Graph the equations x equals 5, x equals 2, y equals negative 2, and y equals 1. What enclosed shape do the lines form? Explain your reasoning. Given that they're only vertical and horizontal lines, it's either at least a rectangle or at most a square. So we'll figure out what this thing is here. So x equals, let's write those, x equals 5 is going to be this vertical line going like, oh, I'm going to draw them back to arrows and such. They're talking about how the points of intersection go, but I'm going to draw that entire line that looks like this, x equals 5. Now we'll have x equals 2. That's another vertical line. It's positive 2. So that's right here, going down 2. Y equals negative 2. It's a horizontal line going across negative 2 for y right here. This is where y is negative 2, going across like that. And then y equals 1 is a horizontal line going across 1 like this. So again, where these intersect like this, we form a shape. Now, this could be a rectangle because it has all right angles, but I'm thinking even more so, it looks like all the distances around this object are 3s. This is 3 up, 3 left, 3 right, 3 down. and all right angles. Guys, this is a square. This is a square. It says explain your reasoning. All angles are right angles because vertical and horizontal lines are perpendicular to each other, and all side lengths are 3. All side lengths are 3, and all angles are right angles because horizontal and perpendicular lines are, or horizontal and vertical lines are perpendicular to each other. Yeah. Okay. Yeah. Okay, number 34. How do you see it? This is going a little bit longer than I expected. How do you see it? You're organizing a class trip to an amusement park. That is just the best. The cost to enter the park is $30. The cost to enter with a meal plan is $45. That seems reasonable. You might want to use it. You have a budget of $2,700 for the trip. Here's the equation. Well, they're not having us make our own equation, so I guess that's another day. This equation models the total cost for the class to go on the trip. This is based on which students, because X is the number of students who do not choose the meal plan, Y is the number of students who do. So this is based on which students are going to not meal plan and yes meal plan, and as a total, you're going to spend this much money. So, yeah, anyway. Okay, so here's the graph. So they did it for us. How did they come up with these? The y-intercept, they divided 2,700 by 45. Apparently you get 60. They divided 2,700 by 30, and you get 90. So those are parts of them. It says interpret the intercepts of the graph. They ask, how do you see it? Well, the way I see the intercepts is that you could have all 60, is it all 60 students? Okay, to fit within budget, This is kind of an interesting question because this varies the number of students that we have. It seems like we're changing the number of students with this. But to fit within budget, we could have 60 students. Choose the meal plan option. Plan pass, what is it called? Just the cost. The meal plan option. And no students. Choose the non-meal plan option. Or we could have 90 students go no meal plan and no students go meal plan. Kind of sounds weird that way. Now, the interesting part about that, right? It says you're organizing a class trip to an amusement park. If you want more students to go, I mean, it's either making them starve or pay for themselves or whatever it is you're going to do. If you want more students to go, you're going to have less to go to the meal plan. This is kind of an interesting question because the number of students is varying here. That's kind of weird. It's like, all right, Martin, you can't go. Sorry, Letitia. You know, it's like you're limiting who can go and who can't. So, Neil, we can only spend $2,700. Now, put that extra $15 away. You can't eat, Neil. Right? It's interesting. Part B, describe the domain and range and context of the problem. So the domain, first of all, because here's the thing, we're not going to write the domain and range. When it comes to this is number of students. That means it's technically discrete. It could be 0 or 1 or 2 or 3, or maybe not exactly those whole numbers, right? That might not fit right within the 2,700 exactly, but it's a list of values. So the domain does have to do, though, it's actually right here. It's the number of students who do not choose the meal plan. So the domain is the possible number of students. Do I have caps lock on? The domain is the possible number of students who do not choose the meal plan. Now, that spans 0, maybe 3, 6, 9. I don't know what the actual numbers can be, but that's the domain. The range is the possible number of students who choose the meal plan. That's describing the domain and range of the problem in the context of the problem. Okay, number 35. Reasoning. Use the values to fill in the equation here so that the x-intercept of the graph is -10 and the y-intercept of the graph is 5. Now, we won't play guess and check on this thing, and I kind of want to give like an algebraic setup for this. This x plus this y equals 30. Honestly, I want to say like ax plus by equals 30. Okay, remember for our x-intercept, we would, well, hold on. For our x-intercept, we would set y equal to 0. That means some number times x is 30. So we would divide both sides by a to get the x-intercept. X is 30 over a. So that means 30 divided by a, guys, has to equal, what is it? Negative 10. So 30 divided by what number gives you negative 10? Now, we haven't done really a lot of problems with variables in the denominator. I don't know if we've done any in the denominator. So for now, let's just kind of play guess and check. 30 divided by what is 10? 3. Making it negative? Negative 3. So our value here has to be a negative 3. I'll change it to a negative 3 here. Negative 3. And for the y-intercept, again, you set x equal to 0. You get b times y is 30. Divide both sides by b. You get y equals 30 over b. So 30 divided by some number here is giving us 5. That would be 6, right? That kind of looks like a 6. So your y-intercept, not your y-intercept, your coefficient for the y guy there is 6. So negative 3 and 6. Oh, there are options right here. Oh, we could have probably done stuff like that. I just want to give more algebraic setup so we're making more sense of this is how we would have found x-intercepts anyway. But now that we have it, here's how we can find the number. It's not often that we write equations in standard form from a graph or from intercepts. That's a little trickier to do. I do want to stress that. That question is uncommon. Number 36 on thought-provoking. Write an equation in standard form of a line whose intercepts are integers. Explain how you know the intercepts are integers. Okay, I get to come up with my own equation. I'm going to make up my own numbers here. I'm going to say 2x minus 6y equals. In order for this to work out, for them to be integers, remember, when we find intercepts, we divide this number by 2 for the x-intercept, this number by negative 6 for the y-intercept. That means my number here needs to be divisible by both 2 and negative 6, which is another way of saying it needs to be divisible by 6. Because, number 1, negative doesn't matter, and number 2, anything that's divisible by 6 is divisible by 2. I need an even number, divisible by 6. I can do 6, 12, 18, 24. I'm going to do 24. I could do negative 24 or whatever, but this is why. So 24 is divisible by both 2 and 6. So that's what you have to do. Just come up with something that's divisible by both. The x-intercept is 12, the y-intercept is negative 4, right? That's the reason why that works. Number 37, are the equations of horizontal and vertical lines written in standard form? Explain your reasoning. They are, and that's really where they came up with this thing here. Yes, when I have some sort of x equals h equation or y equals k, keep in mind that x equals h is some sort of 1 times x plus 0 times y equals whatever that h value is, and y equals k is the form of some sort of 0 times x plus 1 times y equals k. Even if, see, what they did in the lecture portion, even if you had a number for y like a 4, and this was 40 or whatever, you still divide it by 4 and it's still a y equals equation. But yes, this takes on the standard form appearance, even like this, with these letters, involved. You don't have to worry about the h and k. Those are just numbers, right? Constants. Those are that. So these terms go away and you're left with just that. X equals h, y equals k. So yes, they're in standard form. The thing about standard form, again, the beauty about the form itself, they are both on the same side of the equation. Both variables are on one side of the equation. Both variable terms, I should say. Both variable terms are on one side of the equation. And the constant is on the other side of the equation. A y equals equation is when x equals 0, and an x equals equation is when y equals 0. So those other variables go away. Both variables may be on the same side, but one gets to go away just like that. Whereas, y equals mx plus b, and this is, this is just going into our next section. And y equals mx plus b, I'll tell you what, the y-intercept is pretty easy to find. You set x equal to 0, this goes away. But for the x-intercept, you have to set y equal to 0. We have more math we got to do. We got to move this term over or this term over. It's up to you. There's just more to do in that situation. And oftentimes, m will be a fraction. It gets a little weird. There's something about standard, and I didn't mention this. I didn't mention this, and you know what? The book didn't mention it either. Probably because of the way they set up some problems. Something about standard form that tends to be the case is that A, B, and C, they said that they can be constants, whatever. A, B, and C are generally integers. They're generally integers. And more often than not, especially when I write an equation, A, the term for X, is generally a positive number. So you won't have something that says like 1/2 X plus 3/5 Y equals, whatever, 2/3. You would actually have the bigger version of this answer that it would be. If I multiplied everything here by, say, 30, the least common multiple, it would actually say 15x plus 18y equals 20, right? This wouldn't be standard form. This would. Actually, I could divide those all by, no, that's right. So 15x, so anyway, that's the point of that. I know I'm going a lot on that problem, but I really want to teach you some of the things that standard form will have for reasons that we might like it more in situations. The last question is number 38 on abstract reasoning. It says the x and y intercepts of the graph of the equation 3x plus 5y equals k are integers. Describe the values of k. Explain your reasoning. So we have intercepts that are integers here. We need to divide k by 3 at some point and get an integer, right, for the x-intercept. X-intercept is k divided by 3, and the y-intercept is k divided by 5, right? That's kind of what happens on those ones. In order for this to work, our k value needs to divide by both 3 and 5, which means the least common multiple of 3 and 5 is 15, which means k needs to be some multiple of 15. K needs to be some multiple of 15. It is the only way, even if it's negative, even if it's 0, even if it's negative, it is the only way that it can divide by both 3 and 5. Okay. And that's something that you might notice, right, when the equation's set up. That's what I talked about in the graphing problems. How do I know something's an integer? I can't divide 20 by 3, even though I can divide it by 5. The x-intercept's going to be a fraction. So that's kind of the things that we saw. All right, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Hopefully standard form graphing's making sense in the equations. We didn't get to write our own equations, and I hope at some point we get to do that, or that's probably saved for a whole nother section or whole nother chapter, right? Just another teaching. And I'd understand if it is. But there were the models. We did some of the graphs. We had to change some scales. I have that graph paper down below if you want to use it. I'll continue to have those attached for you. So thank you guys so much. Take care. I'm going to see you in the next one.